Ever had to schedule a new meeting in a busy calendar and wondered where it fits? Insert interval is a Pattern Mastery 100 staple, loved by Google, Amazon, and Facebook to test your interval merging and array traversal skills. Over 30% of candidates stumble on edge cases, especially when the new event overlaps with many intervals. Master this and you'll breeze through scheduling, merging, and range questions in interviews. Let's solve insert interval using the basic approach, so you can handle any interval insertion or merging scenario step by step. You're given a list of non-overlapping intervals sorted by start time and a new interval. Insert the new interval, merging if necessary, so the output remains non-overlapping and sorted. List of intervals, each as start, end, sorted, non-overlapping new interval, start, end. List of intervals after insertion and merging. Think of adding a new meeting to a packed conference room schedule. You have to insert it in the right spot and merge if there's any overlap. Interviewers might ask, how would you efficiently handle time slot insertions in a shared calendar app? What's tricky? Need to merge if new interval overlaps with any existing. Carefully handle cases where the new interval is before, after, or in between intervals. Avoid unnecessary merges, stick to intervals that actually overlap. Loop through existing intervals. If current interval ends before the new interval starts, add it to output. If current interval starts after new interval ends, add the new interval, then the rest of the intervals, you're done. If there's overlap, merge, update the new interval start to min_cur.start, new.start, end to max_cur.end, new.end. Add any unmerged new interval at the end if needed. Let's clarify. The output must be sorted and non-overlapping. At most one merge run is needed, since input is non-overlapping and sorted. Edge cases. New interval before all others. New interval after all others. New interval overlaps multiple intervals. Initialize an empty result list. Iterate over each interval. If current ends before new starts, append current. If current starts after new ends, append new, then append the rest and return. If overlap, update new interval to merged range. After the loop, add the last new interval if not already added. Return the result. Let's implement solution 1. Insert interval with merge strategy. Define a solution class as a wrapper. Takes a list of sorted, non-overlapping intervals and a new interval to insert. Append the new interval to the list. Sort intervals by start time to make merging easier. Initialize list to store merged intervals. Loop through intervals and merge overlaps. No overlap. Full overlap. Return merged list with new interval inserted and overlaps combined. Insert interval adds the new interval, sorts, and merges overlaps efficiently into clean, non-overlapping ranges. Test input. Intervals equals 1, 3, 6, 9. New interval equals 2, 5. 1, 3 covers 1 to 3, 6, 9 covers 6 to 9. New interval 2, 5 overlaps with 1, 3, but not 6, 9. Why the solution works. Algorithm steps. Add new interval and sort 1, 3, 2, 5, 6, 9. Merge overlaps. 1, 3 and 2, 5 overlap merge to 1, 5, 6, 9 starts after 5 append as is. Final merged intervals 1, 5, 6, 9. Program outputs 1, 5, 6, 9 matching expected. New interval inserted and overlaps merged efficiently and accurately. Solution 2. Insert interval using single pass merge. Define a solution class as a wrapper. Takes sorted, non-overlapping intervals and a new interval to insert. Initialize result list to build the final merged intervals. Pointer I iterates through intervals, n is the total count. Phase 1. Add intervals before new interval. Copy intervals that end before new interval starts, no overlap. Phase 2. Merge overlapping intervals. Extend new interval to cover all overlapping intervals. Add the fully merged interval to result. Phase 3. Add intervals after new interval. Append remaining intervals that don't overlap. Return result, all intervals before, one merged interval, then remaining intervals. Single pass, on time and space. Algorithm efficiently inserts and merges the new interval in one pass, keeping intervals non-overlapping. Let's test our function using the intervals 1 to 2, 3 to 5, 6 to 7, 8 to 10, and 12 to 16, and a new interval 4 to 8. We want to insert this new range and merge any overlaps. 1 to 2 covers time 1 to 2. 3 to 5 covers time 3 to 5. 6 to 7 covers time 6 to 7. 8 to 10 covers time 8 to 10. 12 to 16 covers time 12 to 16. The new interval 4 to 8 overlaps with 3 to 5, 6 to 7, and 8 to 10. Copy intervals before the new one. 1 to 2 comes before 4 to 8, keep 1 to 2. Merge overlapping intervals. 3 to 5, 6 to 7, and 8 to 10 all overlap with 4 to 8 merge into 3 to 10. Append remaining intervals. 12 to 16 stays as is. Output the final merged intervals are 1 to 2, 3 to 10, and 12 to 16. Our function correctly inserts the new interval and merges overlaps. The result is 1 to 2, 3 to 10, and 12 to 16. Clean, accurate, and efficient. Let's have a quick recap. We're given a sorted list of non-overlapping intervals and a new interval to insert. The goal is to place the new one correctly, merging it with any overlaps so the final list remains sorted and clean. It's all about managing order and boundaries efficiently. The challenge comes from the overlap logic. You need to handle 3 scenarios: when the new interval is before all others, after all others, or overlaps one or several intervals in the middle. The trick is merging only when necessary, not overcomplicating what's already sorted. Here's the plan. Loop through the intervals one by one. If the current interval ends before the new one starts, just add it to the result. If the current one starts after the new ends, add the new interval, then the rest, and you're done. If there's overlap, merge by taking the min start and max end, and keep going. After the loop, add the final merged interval if it hasn't been added yet. We followed this linear plan, merged overlapping intervals smoothly, and kept the final list sorted. The code ran on LeetCode successfully. No errors, no missed cases. After running the solution, every test case passed perfectly. The logic handled overlaps, gaps, and edge positions exactly as expected. All outputs matched. The key takeaway? Smart traversal beats complexity. By respecting the sorted order and merging only when needed, you can turn any scheduling or range insertion challenge into a simple, predictable one-pass solution.